So the first statistical test that I want to talk about is chi-square, and this is a little bit unique. It still is doing something similar to the rest of them, but it's a little less of kind of the straight hypothesis testing. This is basically trying to determine if something is different from what's expected. So it's not necessarily comparing two different groups, it's comparing a group with what you might expect that group to be. So in a way you can think of the expectations as, I guess, the control group, and you're seeing if your test group is different from the control group, but really it's more testing if your predicted hypothesis was correct or not. So let's think about this for a second. All right, so what the chi-square actually does is it really compares the distance from your observed value from your expected value. So how far away is your observed value from what you might expect, right? And then, so you can just look here, and I don't want to get too much into the math, but this is the chi-squared. This is the sum of each individual observation. So what's your observation? How far away is it from the expected, right? And then it's squared. That means that if your observed value is below or above expected, in the end it's going to end up with a positive value no matter what. Then you divide it by your expected to really bring it back down to a single, not a squared exponential value, right? So you have to square this in order to get it positive no matter what. Then you divide by your expected, and then you sum that for every observation. So the more your observations consistently are different from what you expect, then the higher that chi-square value is going to end up being. Right? So it's taking that distance from the expected value, and it's taking the sample size, and it's going along the way. All right? So, again, this is basically used to tell how well your data fits to a predicted distribution. So the hardest part of this chi-square, especially when you're using Excel and you know how to do it, it's not doing the chi-square itself, it's thinking about what your expected values should be, because you have to create your expected values. What was expected in order to really see if you're different from that expectation or not. So one of the things this is often used for, and you probably have heard about this through genetics, this is used all the time in genetics. So for example, if you think a trait is detrimental, then that trait might be less frequent in the genetics than you would expect just by Mendelian genetics alone. So you can figure out what your Mendelian genetics would predict, and then you can take the number of observations and see if that is too far away from your prediction, from your expected, to be just random variation. All right, so that's what chi-square is doing, because you expect there to be random variation, so your observed is not always going to be exactly as you're expected. We saw this with sampling error, right? So you would expect there to be a 50-50 ratio of males to females, but that doesn't mean that your observed in any given family is always going to have one male, one female, or 2 and 2. There are some differences along the way. So chi-square is saying, are you too far away from the expectations to be accounted for just by random variation? All right, so let's take a look at this on the Excel file, and we'll talk this through a little bit as well. All right, so I'm going to pull the Excel file over here for us. This is the one that you should be able to see in your student's Excel file. And so while I have a little bit of time, I'm just going to look at the bottom. So look at the bottom of your tab, and you'll see, or the bottom of your Excel file, sorry, and you'll see many tabs. And each of these tabs is a different test that we're going to work on together. And then for some of them, I'll show you how to do it together, and then you have one to do on your own, kind of as homework. And then how to do it together, and then one on your own, and so forth. So pay attention to those tabs along the way. And let's talk about how to do this with our chi-squared. So here we have all the different Aries, Taurus, Gemini, Cancer, and so forth, right? So we have the different, oh man, I'm blanking on what those are even called. But anyway, you know what I'm talking about. So this is observation, so basically looking at a large class of students, how many of them were Aries, how many were Taurus, and so forth. Now, so we can take a look at this, and we can figure out how many data points we have. So equals count. Figure out my number of data points, and as you might expect, we have 12, all right? we also know that we can figure out the sum of all these values. So how many observations did we have? So in order to do that, I need to type in sum. And to figure out how many observations I made total, I'm going to get the sum of all those observations, and you'll see that I made 256 observations. Now, there's no reason to think that there should be more Virgos than there are Leos, or any one of these should have more students than others, because they're all the same length, right? So we would expect that all of them to have an equal number of these 256 observations. So I would say the expectation is my 256 observed the observations that I made divided by the 12 different time frames. So 256 divided by 12 means that each one should have 21 1/3 people in it approximately. All right, so we would just basically say 21.3 is our expected number that would be Aries. And that same 21.3 would be expected for each of those. So now I have my observations here, and I have my expected amounts. Because again, let me just explain that one last time. I would expect there to be an even distribution of people that are Aries, Taurus, Gemini, and so forth. So of my total number of people divided by the 12 different time frames here, then I would expect 21.3 to be in each of them. All right, obviously you can't have 1/3 of a person, but this is the statistics. That's this number divided by 12. That's what I would expect. Now, again, that's the hardest part. So how do you get your expectations? Once you have that, chi-squared is pretty easy. You just go equals chi, and you start to look for chi-square test. All right, so down here, chi-square test. Double click on that, and you'll see the actual range means your actual observations. So here's my actual observations, right? And then, comma, the expected range. And you can see here that my chi-square value is 0.926. This means there's a 92.6% chance that these data are the same. So there is not a reason to believe that this data is different from each other just because other than random variation. So in other words, it's telling me that Virgo is not actually an outlier low. Aries is not actually an outlier high. Within random variation, this fits my expected values enough to the point of 92.6% chance these two are the same, right? So my chi-squared value says these are not different from each other, right? But let's take a quick look here. What if I did have an outlier? So I'm gonna, for the moment, change Scorpio right here to 42. So let's say I had made 42 observations there. You can see that my sum of observations went up, my expected goes up, so now I actually need to change that expected to my new expected, 23.2. That would be expected for all of them based on the fact that I had more observations. But you can see now, that was such an outlier there. That was such an outlier that my chi-square is now 0.03. That means there's only a 3% chance that this data falls within my expected range within random variation. It's telling me that somewhere in here there is an outlier, and this is not. This only has a 3% chance to be what I expect, and therefore it has a 97% chance to be different. That's what the chi-square is telling me. It's telling me that somewhere here there is an outlier. And maybe that outlier is the fact that 9 months before this, we had a COVID-19 outbreak, and therefore there was a lot of kids born as Scorpios pretty soon. Who knows? But there's something that made this different from what we would have expected when our expectation was that they should all be even. That's what chi-square is telling us. So what I'm going to have you do here, you can read through this. This is what you're going to do on your own. But we're looking at red, spotted, white. We would expect a 1 to 2 to 1 ratio, right, of these, because there should be 25%, 50, 25. And we are trying to see if there is something in San Diego that's causing selective pressure against the white flowers. So in other words, does the observed values here, and you need to create the expected, you need to think that through, but when you have the expected, are our observed values close enough to expected to say that this is just random variation? Or is there indeed something to tell us that the observed is different from our expected, and therefore maybe there is something selecting against white?